Hello again. What we're going to do is we're going to take a look at translation. This is going to be part one of a short series of videos on translation. In this one, the main goal is just to talk about how do we go from a DNA sequence to an RNA sequence, ultimately to a protein sequence. Some of you may be familiar with this if you've taken biology in the past or have taken genetics or microbiology, but I just want to use this as an opportunity to review this concept. So let's take a look at this sequence here. What we're looking at is template DNA. And remember, template DNA and mRNA are complementary and anti-parallel to each other. So for example, what that means is if this is our 3' end of the template DNA, then our mRNA needs to start with a 5' over here. And now we're going to write down the complementary base pairs. In mRNA, T's from a DNA template pair with an A, A's pair with U's, C's with G's, and G's with C's. And so if we finish out the rest of the sequence, this is what we will get. And so the question then becomes, how do we take the sequence and convert it into a protein sequence? Or an amino acid sequence. And one thing to note here is that mRNA is read in what we call a triplet code. And that triplet code basically means that from a start codon, which this AUG is, we can actually divide the mRNA sequence into 3-letter codes. Each of these is known as a codon. And each codon encodes for one amino acid. And there are 20 total amino acids that are coded for by 64 potential codons. So let's take a look at how do we use a codon code and how do we use a graphic organizer of these codon codes to determine an amino acid sequence. And so I bring you to this particular table right here. There are also codon codes that are circular in nature, but for AP Biology, we're going to use this format here. This is set up so that every one of these codons you see are written from the first letter at the most 5' end to the second to the third letter, which is at the 3' end of the codon. And so if we want to look for AUG, we'd start out with the A's here, go to the U's, and then find our AUG, which is located right here. And this codon codes for the amino acid methionine, or which is abbreviated MET. But I also want to point out that this is also known as the start codon. And so AUG serves a dual function here. And so what we're going to do is instead of writing start, we're just going to write MET as the amino acid that is coded for by AUG. Now if we do the same process again and now look for CUC, let's go back to our table. And so we're going to look for CUC at this point. And so if we look for CUC, again, we're going to start with our first letter being C, our second letter being U, and our third being C, and that is located right here. And you can see that any of these, CUU, CUC, CUA, and CUG all encode for the amino acid leucine. And so there's some redundancy in this code. So let's go back to our previous slide again. Our second amino acid is then going to be the amino acid leucine, or LEU. If we follow the same process one more time for GAU, again, we're going to start out by looking for G. We're going to go to our second letter A and our third letter U, and that's going to code for the amino acid aspartate, or ASP. And so if we've done this properly, our protein, or our amino acid sequence from the beginning of the mRNA to the end of the mRNA that we're looking at here is going to be methionine, leucine, and aspartate. A couple of things to recall real quickly. The mRNA is read by the ribosome always in a 5' to 3' direction. And so if you ever see the mRNA written in an opposite direction, where the 3' end is on the leftmost side and the 5' end is on the rightmost side, you may want to physically flip the whole sequence and rewrite it from 5' to 3' so that you can easily decipher the amino acid code.